Neil, welcome to week 10 of the economics of cryptocurrency. I'm going to jump right into some stuff today because we're going to do something exciting as far as I'm concerned. We're going to look at this chart to start, well, not quite to start off. We're going to look at this newspaper article because I thought this connected to some stuff that we've discussed. The hottest new crypto trade is 24/7 oil futures. So I don't think I required you to read the section of the book called Digital Tokens, but that would be a good chapter to connect or part of the book to connect to this article. Just a couple things. This is sort of related to, remember, we talked about being able to buy silver futures from a blockchain like Ethereum. And those are really what are called tokenized silver futures. So you're not actually trading silver futures contracts on the Chicago Mercantile Exchange, which would be one common traditional way to do that. Similarly, now this company called Hyperliquid, right here, lists perpetual futures, which basically allows people to trade oil, traders or speculators to trade oil when the traditional markets are not open. So 24/7. One thing they talk about down at the bottom, the ability to trade these assets 24/7 with leverage. That means we can borrow some extra money. So we might put collateral like Bitcoin, um, show that we have that into a collateral pool somehow on a blockchain in a variety of different ways. And then we'd be able to borrow actually more than that collateral usually. That would make it leverage. And then with that borrowed money, we could bet on things like silver futures was our example from the past. Now we're talking about oil futures. So this paragraph just says like that could be really risky, and you guys understand perfectly why now, because you could do that same exercise we went through with silver futures. Think about that in the context of oil futures. Oil futures, of course, have been very volatile recently as a result of geopolitics and events in the Middle East, Iran. Um, and the types of traders that trade crypto generally like volatility, so they're attracted to that type of thing. Interestingly, you cannot do this from the United States currently, due to regulations, but eventually probably you would be able to do that from the United States. So, and also on blockchains, maybe you can do it from the United States on which blockchain you're working with because it's relatively easy to hide your identity. It's relatively easy to hide your location, things like that. So I'm not saying you should do that, but I imagine that some people have figured out how to do things like that using current technology, but you're not technically allowed to trade on this market from the United States currently. So I thought that was just an interesting article that relates to current events and relates a lot to what we've been learning about in class. Now, today we're going to talk about, so Zcash is another cryptocurrency, kind of like Bitcoin or Ethereum. But this one is a privacy-focused cryptocurrency, which features an encrypted ledger using zero knowledge proofs. On Zcash, transactions can be transparent and publicly viewable, or they can be shielded transactions, which use the type of zero knowledge proof to provide anonymity in transactions. Now, this is a good week for us to be talking about this because last time we did Corda, which is a permissioned blockchain, and we cared about certain things like trade secrets. Maybe that certain types of trades and transactions I want to make, I need those to be private because have to do with my business model. And that's not quite achievable. I mean, it's achievable maybe in some ways and in some sense on Bitcoin, a permissionless blockchain. I'm sorry, I don't know. Corda is permissioned. Bitcoin is permissionless. So what we're going to talk about today is we're going to go through really these zero knowledge proofs and talk about maybe we can get some of those benefits that we talked about with Corda on publicly verified blockchains like Bitcoin, which kind of Zcash represents. Now, it's not, there's going to be trade-offs still, so it's not all going to be perfect, but this idea is sort of on the cutting edge of crypto. It's been around for a while, but a lot of interest in Zcash and the privacy preserving blockchains nowadays. So let's go ahead and take a look at this crazy chart right here. This is what's called the Alibaba Cave Challenge. And it's an example used. So we're basically going to cover this thing called zero knowledge proofs today. And really, we care about the intuition. There's quite a bit of math in zero knowledge proofs, as we'll go over. But this is designed, this story is designed to give you the intuition about how zero knowledge proofs work. And then we're going to go into the Colab and you'll see the math behind. But really, what I want you to think about is that math we're going to go through is basically an example of what's going on in this somewhat complicated chart, which I'll explain now. So we basically have the underlying idea of zero knowledge proofs is we have somebody called the prover, in our case, Peggy. Peggy may or may not have a secret password that can open this door right here in the caves. So she is the one that may or may not have the secret password. We'll assume she's claiming she does have the secret password, and she wants to prove that. But she wants to prove that without providing any extra information whatsoever to Victor, who's the verifier. That's the person that she wants to be able to prove that she has the password to, but without really providing any other extra information. In particular, she wants to prove to Victor that she has the password, but not provide him the ability to prove she has the password to anybody else. So that's kind of the underlying motivation for a zero knowledge proof. So let's think about what's going on here. This is a cave, a very detailed graphic of a cave. This is the entrance. And importantly, the entrance turns, so Victor cannot see what's going on down in this part of the cave. And there's two sides of the cave, side 0 and side 1. Now, Peggy is going to go into the cave. She wants to prove she has the password to get through this door. She's not going to just tell Victor the password. She's not going to just walk through from one side to the other because that would be sort of too direct proof. And if Victor had evidence that she had done that, then he would be able to pass that on to somebody else. So she kind of wants to do it in a more probabilistic way, we might say. So now, just sort of what's the setup here is that Peggy chooses one of the sides of the cave in this diagram, but she doesn't have to choose side 0. She chooses side 0 just as an example to understand what's going on. So we'll assume Peggy goes down in the cave. She goes to side 0. And then this line is called the commitment line. When Peggy crosses this line, a message goes to Victor saying Peggy has committed. But it does not say what side Peggy has committed to. All that Victor knows is Peggy has committed to a side. Okay? Now, when she crosses back that line, either way to the other side, then Victor will get a message saying which side she crossed her back over. So that's going to be a part, and then the side will be revealed. So, for example, if Peggy goes all the way around and she crosses back over now on side 1 because she's going this way around the circle, which you notice implies that she went through the door, passworded door. Victor doesn't really know that, but Victor will get a message. Victor is notified when Peggy leaves the cave. In this case, Peggy left side B. So he will know which side she leaves, but he doesn't know. All he knows is that she committed to a side. So if she had committed to side B, it's not obvious to Victor that she has the password because maybe she just walked in B, walked back out B. Because again, all Victor knows is that she committed to a side, but not which side. So moving back a little bit, so the number one step, so Peggy enters the cave, chooses a side, and then she commits, which sends Victor a signal. Peggy has committed. So we're going to assume she goes down this side. After Peggy commits, so now she's down here. In my example, she's in side 0. She can easily commit to this side too. But in my diagram, she's committed to side 0. Victor does not know this. All that Victor knows, again, is that Peggy has committed to a side, but not which side. And actually, I'm just realizing that left side 1. I was using A and B before, but I didn't like that, so I changed it to 0 and 1. But this should be she left side 1, sorry. So now Victor is going to, after Peggy commits, Victor is going to issue a challenge. That challenge is going to look like come out through, and then he's going to pick a random side. He's not going to, because he doesn't know what side she's on. And so she's going to come through a random side. So in our example, we'll assume that the challenge was come out through side 1. And then she comes out, and then here we go. He gets a message back. Victor is notified Peggy leaves the cave, in this case, side one. Now, there's possibility of cheating here because just in my example, she committed to side zero. We know that she must have had the password because we can see things that Victor can't see. She went through side zero and then she came out side one. The only way to do that is to go through the passworded door because remember, she can't turn around and cross this line again without notifying Victor. So in that in this case, we know she must have had the password. Victor doesn't know. But Victor can now say there's a 50% chance that Peggy had the password because it's possible that she does. The one possibility in Victor's mind is what we see happened, and that implies she has the password. However, the other possibility that because Victor can't see what's going on inside this cave is that she actually went in on side one, committed, and then just came back outside one from the challenge. Now, the reason that this can work is Victor can say, okay, we're going to do this again over and over again. So if she goes again, maybe she commits to the same side again, and then he issues a challenge. Maybe the set challenge is side one again. And so then if that keeps happening, if she keeps successfully exiting the side after commitment that's consistent with the challenge, the probability that she's cheating must be decreasing over time. And that's the way fundamentally a zero knowledge proof works, is that if you do repeated trials, and we'll see this later, repeated trials, or we could expand the scope of challenges available to Victor. Here, there's only two possible challenges, come outside zero or come outside one. So each time, if Peggy's really lucky and doesn't have the password, maybe she's committing to the same side as the challenge, but eventually the probability that she's doing that correctly over and over again gets really small if she's a cheater, which means the probability that she truly does have the secret password is getting higher and higher each time she's challenged to do this over and over again. So Victor can become convinced that she has this secret information not only without ever revealing the secret information, but without even revealing what she's committing to. Because remember, she's not revealing what side. It just says Peggy has committed to something, but not what side. Now, the reason I'm showing, and this is a very famous example, so it's not my example, but I'm showing you this because this one's a little bit complicated. Think about it, what I just described. But this is definitely easier to capture the intuition of than the math we're about to go over in the collab. But I want you to connect that. I really want you to see, look, this math we're going through is a very similar sort of commitment challenge type algorithm as this Alibaba cave example. Important note, I mentioned this at the beginning, and this should be side zero and side one, sorry, instead of A and B. So in this example, Piggy commits to side zero because that's just how I drew it and leaves side one, indicating she has the password, but there are other potential outcomes. We could draw the example of this if Peggy didn't have the right password. Suppose she commits to this side and then the challenge is side one, but she's a cheater and doesn't have the password. She can only leave the cave. She doesn't want to die in the cave. So the only one, like, all right, I'm going to have to give up. So I'm going to cross back on this side. She will fail the challenge in that case. It's possible that she does side zero, challenges side zero. She passes the challenge. We don't know if she's a cheater if she has the password yet. Victor also doesn't know, and he can't even see what we see, but even we don't know looking inside the cave if she has a password because she didn't have to cross the threshold. That's one of the reasons you need repeated trials to become more certain of what's going on. Because if you do this over and over and over again, if she's a cheater, she's going to run into a challenge that she can't beat eventually. If she does actually have the secret password, she will be able to meet every single challenge because she can just come out the same side she walked in, or she can go through the door when necessary based on the challenge after commitment. And that order is very important. So let's go ahead and take a look at this week's collab. So zero knowledge proofs and privacy preserving verification. So early in this course, we studied several ways that economic systems verify transactions and coordinate shared records. And we sort of compared and contrasted when we brought in Corda between Bitcoin and Corda. Bitcoin is permissionless participation. Identities aren't shown because I don't want to try to pronounce that word on video. Global broadcasts of transactions. That's how we get verification. Hey, look, everybody, here's the entire history of everything. You can literally track this coin through its entire life. Verification by anyone. Agreement through proof of work rules, as we've discussed heavily in the past. So verification works there because everything is public. Anyone can independently check the ledger and confirm that the rules were followed. In a core-style system, a permissioned participation, like we talked about last time, so we have legally identifiable institutions. We mentioned things like banks, hedge funds, pension funds, financial institutions that are like, hey, prove this is me. I'm going to have an account here. You're not going to necessarily share that I have an account here, but I'm going to approve to a centralized third party, basically, a trusted third party, that this is my identity. Selective information sharing. So here we really have, other than the disentanglement between identity and addresses, we have open information versus in Corda, we have selective information sharing means we have a lot of private information, like one-to-one transactions that nobody else can see. And that's because we maybe want to protect trade secrets or business secrets or things like that. So verification there happens through digital signatures, and then there's a notary service. So that's when we're bringing in the trusted third party. We're replacing everything as public with a notary service. Corda gives up the no trusted party property of Bitcoin. Instead of public verification by everyone, it introduces a notary, again, a trusted third party that ensures that states are not double spent. Because so remember, states are how changing states are how transactions occur in the Corda system. So there's an important design trade-off that lives here. Bitcoin achieves verification through public transparency. Corda achieves verification through institutional trust and selective disclosure. Those are very different things, and they have major trade-offs. Both systems solve coordination problems, but they do so using different institutional structures. Zero knowledge proofs maybe can are a third way that maybe gives us back some of the characteristics we like from both of those systems. So zero knowledge proofs introduce a new possibility. Instead of making information public like Bitcoin or relying on a trusted institutional verifier like Corda does, a system can allow someone to prove that a statement is true without revealing the underlying information. Like in our Alibaba Cave challenge that we just went over, Peggy can prove that she has the secret password without revealing that she has the secret password, and even without typing in, like, she's not even typing in the password like this in front of Victor to prove that she has it. He might videotape that or something, and then he's like, look, I can prove Peggy has the password, but we don't even want to be able to do that. And that kind of meets with Corda saying, this is a secret trade I want to make. I want to prove something to my counterparty without showing them my entire balance sheet or something, for example. And zero knowledge proofs might be a way we might do that. So this makes them especially interesting for financial and institutional settings where both privacy and verification are valuable. So some connection to earlier lessons, you can, and of course we're already doing that, but Bitcoin is public verification, Corda is institutional verification, zero knowledge proofs, private verification without disclosure, and we might be able to do that in a public setting. So we could imagine zero knowledge proofs being used in ways that everybody can verify, like Victor, but they can't then learn really anything about that information that's being verified. And that could be quite valuable in certain settings. So economic motivation, many economic interactions involve private information. For example, a borrower may know their financial position, a firm may know its production costs. These are things that firms and borrowers may not want to completely share. An institution may know the composition of its collateral. Often another party needs to verify some condition about that information in order to cooperate or transact, but revealing the entire underlying data may be costly because it could expose things like trade secrets related to production costs, private financial information, regulatory risks, strategic disadvantages. So without a way to verify the condition privately, beneficial transactions may break down because people say, like, look, this is an economically beneficial transaction, but I have to prove something to you that forces me to maybe invest in costly information gathering or just simply provide direct information that I don't want to provide. And the cost of providing that information is greater than the benefit of me entering the transaction. So essentially, we might lose economically beneficial transactions as a result of things like we want to keep trade secrets, but maybe we can find a way to provide the necessary information so that the information sharing costs decrease and we get more mutually beneficial economic transactions as a result. So we can sort of think about this in a game theory aspect too. You don't need a background in game theory, but zero knowledge proofs expand the set of credible signals in games with private information. So suppose one party has private information that we'll call W. Another party must know whether a condition RW equals 1 holds in order to cooperate. So some condition on that private information, another party wants to make sure that condition on the private information holds, like this person does have enough collateral. Without a zero knowledge proof, a ZKP, the informed party must either reveal W, the private information, completely, or refuse to reveal it and lose the cooperative opportunity. A zero knowledge proof allows the party to instead prove RW equals 1, so prove the condition without revealing the underlying information W. So this is still lining up with that Alibaba Cave challenge. It's going to continue to get a little bit more complicated, but if you need to pause, go back, look at that, and continue to tie those connections between that. Think about the Alibaba Cave challenge so that you have the intuition there, and then try to think about that in parallel with what we're talking about here. So a zero-edge knowledge proof allows the party to instead prove, like, I can get through the door without revealing the password. The cost of producing the proof is small enough, the interaction can move to a new equal. If the cost of producing the proof, so this RW equals 1 is small enough, which might be a lower cost than revealing W, the secret information directly, the interaction can move to a new equilibrium where cooperation occurs and both parties are better off. So maybe just reiterating that maybe we're moving into a zone where we can get more mutually beneficial exchanges because parties aren't required to reveal their private information. In this sense, zero knowledge proofs might generate Pareto improvements in environments where verification is required, but disclosure of certain types of information destroys value. So in this CLOLab, we're going to work through a simple what's called a Schnorr style zero knowledge proof. There's many different types of zero knowledge proofs. We're going to use one called a Schnorr style because we can make the math relatively easy to understand and really line up quite closely with our Alibaba Cave example. So the goal of going through this is to understand how a prover like Peggy can demonstrate knowledge of a secret like the password, why the verifier becomes convinced of that knowledge, why the secret itself is never revealed, and how challenge response interactions limit cheating probability. So that's kind of getting at if we do this more and more, we can decrease the probability that Peggy the prover is cheating. We're going to use small numbers in the arithmetic here so it's easier to follow. Real cryptographic systems and zero knowledge proofs use extremely large numbers and more sophisticated constructions because that makes them safer to hack, basically. But the underlying logic that we're going to go through here is the same. So we just have some basic libraries there. So Peggy is going to be our prover again. She's going to have a slightly different type of information, but we could think about that information as a numerical password, actually. So Peggy wants to prove something like, I know a secret X. So X is going to be the secret throughout this thing. And then she's going to also just throw in there that such that Y equals G, which is called the generator, and it could be just a integer or something raised to the power of the secret, Modulus P is a prime number. Modulus, this basically means like divide by P and give me the remainder. So you might want to go take a pause here and go look, whether you've checked modulus before or not. Take a little break, go chat with AI a little bit about what modulus means. It's good for you to understand what exactly this equation is doing before moving on from this step. I'll leave that part to you. But this is what Peggy wants to prove. I know a secret x, so she's not going to reveal the x, such that y equals gx mod p. She will reveal y, but she will not reveal x, of course, because that's the secret, like the password. This is called a proof of knowledge of a discrete algorithm. That's the specific type of zero knowledge proof that we're working through right now. So what's publicly known as a prime p, that's the modulus prime right here. In real system, we're going to use a small prime number in our numerical example, but in general, this will be a very large prime number. A generator function g, so that's right there, and a public value y equals gx mod p right here. So this is just, this y is publicly available. Solving that for x will be extremely difficult. So it's okay to reveal this without, it's okay to reveal this public information. X will still essentially be private. So Peggy knows the secret X. Victor does not know that secret. So setup. So now we're going to just run this through with real numbers. So if you play this, we're just setting numbers here. So our prime is going to be 23. Our generator number is going to be 5. Peggy's secret, x equals 6. This is something that Victor, who's going to be trying to verify that Peggy knows x equals 6 without ever knowing that x equals 6. That's going to be the secret. And then our public value right here, y equals g to the x. So this is just mod p equals 8. So if we throw these numbers into our, based on this, if we throw them in, we get 8. Now in this relatively, because we've used small numbers, it might be relatively easy to solve this, but in general, if we were using huge numbers, it would be quite difficult to solve this problem. So now remember the next step. So this is just a public setup. This is like me showing you the cave, saying like, here's a commitment line right here. Just setting all of that, just setting up, me drawing the cave and stuff. But now what was the next, as the players, the prover and the verifier start to interact, what's the first thing that happens? Well, Peggy committed. She committed by walking into one side of the cave before. In this case, Peggy commits by choosing a random number R. She computes a different value, T equals G to the R mod P. She does not reveal R, by the way, and sends T to Victor. So she generates this and she only sends this new value, T, to Victor. This is called the commitment. Because remember, a message went to Victor, Peggy has committed. Her sending this T value to Victor is that same step. I have committed. Here's my T value that I'm committing to. So it's a little bit, so he's getting some different information. He's getting this T value, but intuitively and logically, this is the same step when Peggy first crosses that line and Victor gets a message saying, I have committed. The key idea is that T reveals information related to R, but it does not reveal R directly, which is important, as we'll see in a second. So she's going to randomly choose R equals 7. And so there's R equals 7, and then the commitment number right here is 17. And we're just applying arithmetic and these mathematical equations that we set up before to get those numbers. So now Victor is going to issue a challenge, just like in the cave example. Victor said, come outside random. And that is there, it's just 0 or 1. We're going to do 0 or 1 again here. So in the simplest binary version, the challenge can be one of two values, C equals 0 or C equals 1. So Victor is going to just send her randomly one of those two values. If Victor chooses randomly, a cheater who prepared only for one challenge has only a half chance of success in that round. Just like Peggy can only prepare for one challenge in the cave, right? Because she can only cross the threshold on one side. And then she has a half probability of meeting the challenge, even if she's a cheater, because maybe the random challenge is the side that she chose. So that is the logical equivalent to here. So a cheater who prepared only for one challenge has only a 1/2 chance in the round. So preparing for a challenge of 0 is like going into one side of the cave and then you would be successful if you happen to get that side of the cave. Because given the challenge, she's going to compute a value based on the challenge. And she already did T. So she already committed to T, and you can see through the math that she can only prepare for one of the challenges through that commitment. And we'll explain that in a little bit more detail below. So let's say Victor's challenge is C equals 1. So then Peggy responds, Peggy computes S, a new number, R plus challenge times X. With small numbers in a single round, the equation works, but real Schnorr proofs reduce the modulo group order. So usually we do the modulus here too. So we're always in mod P. Again, go do a little rabbit hole of mod P if you understand that, but it kind of just resets. So we're always counting. We're like recycling through our numbers from 0 to P minus 1, basically. And I'm happy to talk to you about that if you want to chat with me, because that's a little bit, if you haven't aren't used to that type of math, I'm happy to chat about it with you. So with a small numbers in a single round, the equation works, but real Schnorr proofs reduce modulo the group order implied by the public parameters to keep all values inside the correct mathematical group and also to preserve security in a regular sort of zero knowledge proof system. So now we can compute S here, which is going to be, again, S is R, she chose 7, X is 6, and this is 1, so it's just 7 plus 6 is 13. So now Victor is going to verify, and this is the step where Victor says, okay, did she come out the side that I challenged? It's very easy in the cave example because it's like I said side 0, she came outside 0, check. Or I said side 1 and she came outside 1, check. Or the opposite, I said side 1 and she came outside 0, she's a cheater. She doesn't actually have the password. So this step, this verification step is basically checking her commitment against the challenge and her response to the challenge. So now Victor checks with whether Peggy's response is consistent with the public information and the commitment she sent earlier. So recall from the previous steps, Peggy's secret is X, that was 6. Public value Y, G to the X mod P, that was provided up here, is 8. Peggy's random commitment, T equals G to the R. She chose that R. Victor does not know the R. That's kind of like Victor not knowing which side of the cave she entered. He just knows that she entered a cave. He just knows that he sent her this T number. He does not know what the number R is. But then he issued a challenge C, 0 or 1. And then Peggy's response is expected to be S equals R, the number she chose, she doesn't know, plus C times X. And she doesn't know R or sorry, she knows X and R. Victor does not know R or X. So Victor checks whether the following equations hold. G to the S, so that's the number that she sent, so G to the S, S is the new number. Now Victor knows G, the generator. So G to this power, R plus CX, mod P must equals T, the challenge she sent earlier, times Y to the value of C modulus P. And now why this works, so substitute Peggy's response into the left-hand side. So we know G to the S, that's equals G R to plus CX, because that's the definition of S right here, right? So all we're doing is substitution. And remember, S is her response. Victor can calculate this GS number based on her response by just plugging in G to the S, which we know in the algorithm is R plus C times X right here. So we can write this equality. So using exponent rules, of course, we can spread this out. This is G to the R times G to the C times X. And then we can rewrite the second term, g to the cx equals g to the x to the c. And now substituting values we already know, the commitment Peggy sent earlier, g to the r equals t, and a g to the x is y, the public value. So the equation becomes g to the s equals t times y to the c, which is exactly the condition that Victor checks right here. So we're back at the condition that he's checking. You probably should go back through that math slowly. So the intuition behind this is really what I want to get at because this is related to the Alibaba cave example, and this is really the intuitive reason that this proof works. This is zero knowledge proof. If Peggy truly knows the secret X, the verification equation will work automatically. To compute her response, she had to calculate this S equals R plus CX number. That step requires knowing X, of course, right here. Because the challenge C is chosen, I shouldn't say often, is always chosen after she sends the commitment. Because she commits by sending T and then the challenge. So she can only prepare for one of those two challenges, just like she can only choose one side of the cave at the beginning. Victor does not learn X because the only information Peggy revealed about R was T equals G to the R mod P. And notice why we're jumping from X to R here is if Victor knew R and he knew S, he could solve for X basically because he knows C. So then Victor does not learn X because the only thing Peggy did reveal about R was this equation. This would be so she gave him T. Recovering R from T requires solving a discrete logarithm problem. So finding R such that this is true, which is computationally hard when the numbers are large. In our case, you can do it, but we pick very large numbers when we're doing this in a computer system or a cryptographic system. So a cheater who does not know X runs into a different problem. They must send the commitment T before again. So they commit before seeing Victor's challenge C. Once C arrives, they must produce S such that G to the S mod P equals T, which is the commitment, times Y, which was presented at the beginning, raised to the power of C, which of course Victor knows because that's the challenge that he did. And this is an equation that Victor's checking. So does Victor have all of the information to check this? Yes, because he knows S, he knows the generator G, he knows what the prime is for the modulus, equals T, that's the commitment she sent. So she had to commit to this verification before. And then, of course, he knows Y. That was a public value from the very beginning that depends on X. X lives there, and you can only produce the correct Y with X. And then he could raise that to the C, his challenge. And this equation needs to work out Y because of the math we went through right above this. Without knowing X, Peggy cannot generally compute a correct S for an arbitrary challenge. The response must satisfy the verification equation, this equation again, which ties together three values: the commitment, T equals G to the R mod P, the public value, Y equals G to the X mod P, and the challenge C. So it has to tie together those three equations. Because it has C involved, she can really only prepare for one of the two values of C in advance when she commits by sending Victor T. To produce a valid response, Peggy must compute this number. So the value S must be consistent with both the commitment T, which depends only on R, and the public value Y, which depends on X. So she can really only do this if she's the one that sent R and picked R, and she's the one that knows X, or she does in fact know X. A cheater who does not know X cannot generally construct an S that satisfies both relationships once the challenge C is revealed. So you can't commit a T that's consistent with both C equals 0 and C equals 1 in advance. So she's only going to be prepared for one of the challenges. If she's a cheater, she can try to prepare to one for one with zero, and if she's prepared that one and then that's the challenge, she will pass, but she only has a 1/2 probability of being successful because she has to prepare for one or the other. There's also like you can go deeper, like does she know the challenge set? And that can vary a little bit by the different algorithms. So at best, a cheater can prepare in this setup a commitment that works for one specific challenge value in advance. If a victor chooses randomly from multiple possible challenges, the cheater succeeds only with the probability of guessing the challenge correctly before they commit. Just like, I think he's going to pick side zero, so I'm going to go inside zero. And then if he picks side zero, you do pass that round. But if he picks side one, you would fail that round. So there's a 1/2 probability that you would succeed. This is why the protocol convinces Victor that Peggy knows X while revealing nothing about the value X itself. So that's a zero knowledge proof. Through this math and intuition, Peggy, just like the cave example, has proven that she knows X, at least with 1/2 of probability if we do it with one round, without ever revealing X. So now Victor's checks the verification equation. In our example with our numbers so far, Peggy does have the correct X, so it works. So the left-hand side is 21 and the right-hand side is 21. Are those equal? Yes, that's true. So now let's think a little bit about in this example how a cheater can fake one challenge but not both. The simplest intuition is this: a cheater who does not know X may still be able to fake a transcript that works for one specific challenge, but they cannot generally create a single commitment T that will let them answer every possible challenge correctly, just like the cave example. That is why random challenges matter. Because if it wasn't random, maybe we can predict the challenge before we commit, and then that would, of course, be a security issue in this setup. So fake one challenge, cheater prepares for C equals 0. So a cheater can choose a fake response S in advance to make the verification pass for C equals 0. They can simply set T equals G to the S mod P. So let's do fake S equals 9, fake T equals that. So we're just calculating it. Just cheater prepares for 0, chosen fake S equals 9, construct a fake T equals 11. If Victor asks C equals 0, left equals 11, right equals 11, so the cheater passes in that case. However, if he asks the other challenge, that's going to fail. So she was only able to prepare for the C equals 0 challenge in this cell right here. However, she could prepare for the other challenge. What she can't do is prepare for both of them at the same time through her commitment. So she can prepare for C equals 1, pick a face S, and choose T so that G to the S equals T times Y. Therefore, T equals this mod P, and then this is going to work for the C equals 1 challenge, but will not work for the C equals 0. I'm not going to I'm not going to test you on every step of that math. Really, this is about learning the intuition, but I'm sure some of you are interested in that math, so I'm happy to chat about it more. It's one of those things that you really have to just step back and really think about. Start with the cave example, make sure you have the intuition there. Slowly work your way through these examples. You have access, of course, to this collab to really try to, because this is one of those things that's cool. What's one of when you're like, I totally understand this, that's going to make you feel good about your thinking about this problem. So now we can think about, we don't really like, of course, just having like, there's a half probability that that's not a cheater. And so how can we do it? Well, we can do repeated trials or we can have more challenges. So the binary version uses two possible challenges more generally, and we know that it's a 1/2 probability of success to prepare for the right challenge. So if the challenge has two values, cheating probability is 1/2 per round. So we can always fix that with multiple rounds. If the challenge set has 10 values, though, maybe Victor's challenge is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we'd have a 1/10th probability because you can only prepare for one of those challenges in advance out of 10 potential challenges that will be randomly chosen. And then in general, of course, if there's Q different possible challenges, then 1 over Q is our cheating probability. So let's try the same challenge with 0, 1, 2, 3. So Victor chooses C equal 3. Peggy responds with S equals 25 because we're using the same setup. The only difference now is that we have more challenges. And so we can see that if she has the password, then she can prepare for any of those challenges. And you could go play with that and do a different challenge from that set. So why repetition then might matter. So we can either expand the challenge set so there's more random challenges that we might choose from, or we can do more rounds, or we can do a combination of both of those things. So if the challenge set is size Q, then the cheating pro then the cheating probability per round is 1 over Q. Like in the cave example, it's 2. In our simple first example, it's 2. So that's 1/2. But then every time we do a new round, it's 1/2 squared for 2 rounds, cubed for 3, to the n for n rounds. This is why repeated challenge response rounds make the proof much stronger, but more computationally expensive. So that's the trade-off there is we can have more challenges, we can have more rounds. Each time we add in either direction, we get computationally more expensive. We can do a lot more than we've done here at low computational cost. We mainly did the very simple version here, so it was relatively easy to follow the logic. So then here we're just doing some things showing how that probability decreases over rounds, a graph showing, and this is just applying the math that we just went over in those bullets. But importantly, the economic and institutional takeaway, so just wrapping up here, throughout this course, we have seen different ways that systems achieve credible verification. Bitcoin style systems rely on public verification. Transactions are visible to everyone and trust emerges because anyone can check that the rules were followed. Corda-style systems rely on institutional verification, so more traditional types of verification. Transactions are private between known participants, and correctness is enforced through signatures and a notary. So trusted third party right here. That's our trade-off there that we've discussed in the past. A benefit to Bitcoin is lost when we bring in institutional verification. Zero knowledge proofs introduce a third possibility. They allow a party to prove that a statement is true without revealing the underlying information. So maybe we can get a permissionless type blockchain that involves zero knowledge proofs, and we get some of that benefit from Corda back on to a public type of blockchain like Bitcoin. And then we maybe can get rid of our trusted third party in that context. Maybe the public can be verifying zero knowledge proofs like Victor. In this sense, zero knowledge proofs can replicate some of the privacy and verification benefits that Corda provides, but in a permissionless environment without relying on a trusted institutional verifier. So just finally, now we have these 3 different versions. Bitcoin is public verification. Corda is institutional verification. Zero knowledge systems, cryptographic verification without disclosure of the type of disclosure that we see on Bitcoin. We see all of the amounts and transactions. Maybe we can hide that specific information, but still verify in a permissionless environment. So I hope that was interesting to you. This one's worth backing up and thinking about. There's no extra reading. I'd like you to spend your time this week really trying to understand the intuition here and then through the mathematical steps. That really is just a mathematical algorithmic version of this story. If we make her do this many times, then the probability that she's a cheater, if Peggy keeps doing it successfully, is decreasing. If there's more branches to this cave that she might be able to come out of, but it's only one single door, we could imagine drawing it that way, then that would decrease the one-shot probability of success. Because he could issue more there would be a bigger set of random challenges to choose from here. All right, so where we're going next is back onto our sort of Bitcoin blockchain, and we're going to think about the pure microeconomics of blockchains going next. Some repetition of what we've learned in the past, but a little bit more rigorous microeconomic thinking about how that stuff works. So I will see you guys next time. Don't hesitate to reach out if you have any questions, and I'll see you later.